Okay, so we're on problem 17 here now. And we're solving some equations. And these are absolute value equations. So the idea is to lose the absolute value bars right away by applying the definition for removing the absolute value bars. So if I have the absolute value of u equals a, where u is an expression involving x, and I want to lose those absolute value bars, u equals a or u equals negative a. Okay, you always write down two equations when you lose the absolute value bars there. So like in part A, I got 4x plus 3 equals 27, or 4x plus 3 equals negative 27. Okay, and subtract 3, divide by 4. So x would be 6, that's one answer. And then when I subtract 3 over here, 4x equals negative 30, and then divide by 4, x is negative 15 halves is the other answer. Okay, now I see sometimes where students only write down one equation and then get x. Well, if you do that, you've only got half the answer, which is a wrong answer. Okay, so be sure to write down two equations whenever you lose the absolute value bars. Okay, here's another example. So I got 2 times the absolute value of negative 3x minus 2 plus 3 equals 13. Now the first thing I do before I apply the definition for removing the absolute value bars is I got to make sure that the absolute value expression is all alone and on the left. Okay, so let's go ahead and subtract 3 and divide by 2. 13 minus 3 is 10. 10 divided by 2 is 5. Okay, so we have the absolute value of negative 3x minus 2 equals 5. And now when we apply this definition here for removing the absolute value bars, 3x minus 2 equals 5, that's one equation. Or negative 3x minus 2 equals negative 5, that'd be the other equation. So then on this first equation here, if I add 2 and then divide by negative 3, x is negative 7/3, that'd be one answer. And then over here, when I add 2 and divide by negative 3, x is equal to 1, that's the other answer. Okay? You always have two answers when you're solving an absolute value equation. Okay? Now, you can check your answers if you want. Like I'll sometimes see students do this, like oh, you can't have a negative, so they'll throw that away, right? Because anything coming out of the absolute value bars, that's not a negative, right? So x can't be negative. That's not what we're saying though. Okay, x can and will be negative on occasion. Okay. The number coming out of the absolute value bars, that won't ever be a negative. I agree with that. Okay, so there's a difference between what's going into the absolute value bars and what's coming out of the absolute value bars. So like if I just to go back to this example here and check it, if x is 6, 4 times 6 is 24, plus 3 is 27. The absolute value of 27 is 27. Right, so the absolute value notation is used to represent the distance from 0 to a number. So in this case, 0 to 27, that's 27 units. If x is negative 15 halves, 4 times negative 15 halves, that'd be negative 30, plus 3 is negative 27. Okay, the absolute value of negative 27 is 27. Right, because the distance from 0 to negative 27 is 27 units. Okay, so don't cross out that negative and like only circle the positive answer. If you do that, you'll get a wrong answer then. Okay. In part C, we got the absolute value of 8x minus 11 equals negative 7. Well, what I was just talking about here was that anything coming out of the absolute value bars can never be a negative, right? So like in this equation, The left side is some positive number. The right side is negative 7. How many positives equal negative 7? None of them, right? So there's going to be no solutions to this equation, okay? Be aware of situations like that. That can happen, okay? We've also got absolute value inequalities that we need to know how to solve, okay? So in problem 18, I want us to solve each inequality and write your answer using set notation or interval notation. All right, so in part A, we got the absolute value of 5x minus 7 is less than 2. Now, to lose the absolute value bars, whenever the sign is facing away from the absolute value bars, you're going to have a 3-part inequality. Okay, I got a left part, a middle part, and a right part. In the middle, I'm going to have the expression that was inside the absolute value bars, which is 5x minus 7. And on the two ends, I'm going to have the positive and negative. Okay, so negative 2 is less than 5x minus 7. That's less than 2. Now I'm back on more familiar ground here because I don't have any absolute value bars. Okay, and I've got this compound inequality, this 3-part inequality here that I got to solve. So if I split it and say negative 2 is less than 5x minus 7 and 5x minus 7 is less than 2, then on the first inequality, let's add 7. Okay, you got 5 less than 5x. Divide by 5. 5 is a positive number, so I'm not flipping the sign, right? I only flip the sign whenever I multiply or divide by a negative. And it looks like x is greater than 1. Okay, now over here, if we add 7 and then divide by 5, again, 5 is a positive number, so I'm not flipping the sign. Okay, x is less than 9/5. Okay, so x has to be a number that's bigger than 1 and less than negative 7 and less than 9/5. Okay, so here would be that statement written back as a compound inequality, you know, when I put it back together. Now my answer always has to be written either as a set or as an interval. Okay, so as a set, I'd say the set of all x such that x is bigger than 1 and less than 9/5. If I use interval notation, I'd have 1 comma 9/5 with parentheses at both ends, right? Because we're not including either of those numbers there. Okay, so that'd be that one. Now in part B, we have the absolute value of 2x minus 7 greater than or equal to 15. Okay, so whenever the absolute value expression is greater than a number, you're going to have 2 inequalities to solve, just like I had 2 inequalities to solve over here, but the 2 inequalities right here are going to be different. Okay, one of them is like pretending that the absolute value bars aren't even there. So I got 2x minus 7 greater than or equal to 15. Or then the other one is 2x minus 7 is less than or equal to negative 15. So I flip the sign and throw a negative on the right. Okay? Or would be a key word. And there's a difference between the words and or. You know, if I give you a real life example of this, suppose that you're going to go to the ATM to get some cash. Okay, you need 2 things when you walk to the machine, right? You need your card, and you need the PIN, right? Now I think that I don't think I'd like the system that we'd have if we needed a card or we needed a PIN, right? Because now if either one of those things got taken from you, then the other person could access the account, right? So just as that word choice and versus or is important for that one statement, it's important for what we're doing here. Okay. So in the first inequality, when I add 7 and then divide by 2, 2 is a positive number, so I'm not flipping the sign. X is greater than or equal to 11. Okay. Or just go ahead and write that keyword down. That's important. Or yeah, do the same thing on the other inequality. Add 7 and then divide by 2. 2 is a positive number, so again, I'm not flipping the sign there. Okay, so it looks like x is less than or equal to -4. So the answer would be the set of all x such that x is greater than or equal to 11, or x is less than or equal to -4. Now here I've got those two statements flipped. That's okay, okay? The only reason why I flipped them is because usually when you're reading a mathematical statement, usually you prefer to see the smaller numbers first and then the bigger numbers second, okay? You'd still be saying the same thing if you had said the set of all x such that x is greater than or equal to 11, or x is less than or equal to -4. That's the same thing. Let's take a look at part C. So in part C, if I add 2, then the absolute value of 9z plus 1 is greater than 10, okay? I've got a greater than sign, so the key word is going to be or, and I got two inequalities here that I'm writing down. The first one is like pretending that the absolute value bars are not even there. So I got 9z plus 1 greater than 10. Or then the other one is where I flip the sign and then throw a negative on the right. So 9z plus 1 is less than -10. Okay, be sure to lose the absolute value bars at that point, right? Because you just applied the definition for doing that. Okay, and now that's going to be, we're back on more familiar ground here because now I don't have any absolute value bars that I'm using to solve, right? So let's go ahead and subtract 1 and then divide by 9. 9 is a positive number, so we're not flipping the sign there. So it looks like z is greater than 1. Or then when I subtract 1 and then divide by 9 over here, 9 is a positive number, so again, we're not flipping the sign. Z is less than -11/9. Okay, so my answer is going to be the set of all z such that z is less than -11/9, or z is greater than 1. Okay. Now in part D, we have this inequality here. Let's go ahead and get the absolute value of 5 minus x all alone on the left. So if I add 10 and then divide by 3, -1 plus 10 is 9, and 9 divided by 3 is 3. So the absolute value of 5 minus x is less than or equal to 3. So because the sign is facing away from the absolute value bars there, with it being a less than or equal to, then I'm going to have a compound inequality. Okay, so -3 is less than or equal to 5 minus x. That's less than or equal to 3. Okay, and then I can solve this if I add x throughout these three parts, or excuse me, if I subtract 5 throughout these three parts. -3 minus 5 is -8. 3 minus 5 is -2. And then let's multiply throughout these three parts here by -1. So 8 would be on the left, x is in the middle, and 2 is on the right. And I just multiplied by a negative number, by -1. So I got to flip these signs here. Okay. And my answer would be the set of all x such that 2 is less than or equal to x, which is less than or equal to 8. Okay. All right, so we'll go ahead and stop the video right there, and we'll pick up with problem 19 there in the next one there. Okay.